What's up guys, it's Iman Fiaz and today's video is on AKAS Level Chemistry May 2018 Paper 1. Walkthrough only Section A. State two differences between plug-and-plug model and the model atomic structure used today. Current model includes, the current model nucleus includes protons and neutrons, and also the current model electrons are now arranged in energy level / orbitals. Arranged in different energy levels, different / orbitals. Introduce the full electron configuration of atom element R, and R has 7 electrons. So 1s2, 2s2, 2p, 7 electrons, so 4s2p3 then. Identify R. Well, it's got 7 electrons, so I would go here, and then in this case I can't do that, but you go to periodic table, 7 electrons, so it's going to be R equals nitrogen, and deduce the formula of the compound when R reacts with group 2 metal in the same period as R. So you go to group 2 nitrogen, same period as R, and as a group 2 metal, so it's going to be beryllium, and then the formula is going to be Be3N2. Question 2. A 1 gram sample of toothpaste found to contain this much moles of sodium fluoride. Calculate concentration in ppm for the sample of toothpaste, and the concentration expressed in parts per million. 1 part per million represents a concentration of 1 milligram in every 1 kilogram of toothpaste. So I'm going to convert this gram into kilogram by dividing by 1000. With grams to kilogram, divided by 1000. Actually, no, first thing I'd have to do instead of all of doing that is first you find out the MR of sodium fluoride, because the question is all about sodium fluoride. So the MR is 42.0. Now if I want to find out the mass in 1 gram of sodium fluoride in 1 gram, it's moles is the mass of MR, mass is the moles times by MR, so it's going to be 2.88 times by 10 to the power minus 5 times by 42. 1.21 times by 10 to the power minus 3. 1.210 times by 10 to the power minus 3. And that's in 1 gram, right? Then I want to find it in 1 kilogram, so then I divide. No, that's in grams, so I want to get it in kilograms now. So grams to kilograms is times by 1000. I can't believe I just said previously grams to kilograms is divided by 1000. It's not, it's times by 1000. Kilograms to grams is what? Grams to kilograms, I'm dividing by 1000. And kilograms to grams, I'm times by 1000, yeah. So the mass of sodium fluoride in 1 gram is 1.210 times by 10 to the power minus 3 grams. Therefore, in 1 kilogram, is going to be my answer in part 2, 1.2 times by 10 to the power minus 3 grams. 10 by 1000, so I'm going to get 1210, and that's the mass in 1 kilogram, and then into milligrams, well then at 10 by 1000 again, so 1210, and then that is it. 1 ppm represents concentration 1 gram milligram, so then it's 1210 parts per million. Use the maximum mass of sodium fluoride in milligrams that a 75 kg person could swallow without reaching the toxic concentration. 75 kg, 75,000 grams, but then I want milligrams and 10 by 1000 again. No. 3.19 times 10 to the power minus 2 per kilogram, 75 kilograms. So do that first. 3.19 times 10 to the power minus 2 times by 1000 times by 75. Then that would give my answer in milligrams. So 2393. Use the answer to the question to produce mass of toothpaste kilograms of 75 kg person could swallow without reaching toxic concentration. So it's just going to be what my answer to part A was, divided by 2800. I went in kilograms anyway, so it's 0.854. Identified diagram shows correct relative sizes of the ions in sodium fluoride, while negative ions have large ionic radius than positive ions, so it's going to be B, sodium fluoride. Because they both have the same number of electrons. Or isoelectronic, same electron configuration. But the idea that sodium ion has more protons, so stronger attraction for outer electrons. And how many marks is this part worth? 3. So the diagram, that's 1 mark. Then both Na plus and F minus isoelectronic, they both have the same electrical arrangement, but the sodium ion has more protons, so stronger attraction for outer electrons. Use data in table 1 to calculate value for X in the formula Na2CO X H2O. Now, I know that we shouldn't heat a solid sample of sodium carbonate XH2O, alhamdulillah, for 1 minute to remove water and determine a value for X. Figure 3 shows operators used. Table 1 shows the results recorded. Use data in table 1 to calculate value for X in the formula Na2CO3XH2O. Well, what I'd have to do then is work out the moles of sodium carbonate, work out the moles of H2O, and then I can find out X. But in order to find out the moles of sodium carbonate, I need to find out the mass. I know the mass of empty evaporating basin and the mass of evaporating basin on solid before heating. I want to find the mass of sodium carbonate. So it's going to be the mass of evaporating basin and solid after heating, and then the mass of evaporating basin, and that will give me the mass of sodium carbonate. Then I need to work out the mass of water. And I know the mass of evaporating basin and solid before heating and then after heating. So then 0.55 grams. 25.47 minus 24.92. Then I work out the moles. Sodium carbonate to H2O 0.57 over the MR 0.57 over 23 plus 23 plus 12 plus 16 plus 16 plus 16. I get 5.378 3.77 times by 10 to the power minus 3 to the moles of H2O 0.55 divided by 18 0.0305 divided by smallest number molar ratio, so it's going to be my answer 0.0305 divided by 5.377 times by 10 to the power minus 3, and I get 1 to 5.68 molar ratio. Therefore X has got to be 5.68. I think the hardest part of this question is finding out the mass of sodium carbonate and the mass of H2O, and then also understanding how to do the empirical formula method. That method. We divide by moles divided by smallest ratio number of moles. (3.2) The correct value for X is 10, so there's a difference between that and that. Not heated to constant mass. It suggests how the procedure can be improved in the same apparatus given more accurate value of X. Well, I said a difference between experimental value for X and the correct value is not heated to constant mass. So that our procedure can be improved, heat to constant mass. So be sure more of the water more of the water has driven off. Question 4.1. Separate and label solid samples, 3 hydrogen compounds, sodium carbonate, sodium fluoride, sodium chloride, and then let me guess, distinguish them. Yeah, and then you give equations. So stage 1, your suggested tests. So add, I don't know, named acid to all three. Any really, whatever your choice is. Add water. Add silver nitrate solution. That's the test that you're adding, right? Now the observations, which it wants obviously to identify the compounds, observations. Well, sodium carbonate will fizz with acid. Sodium chloride will give white precipitate with silver nitrate. And then the final one, sodium fluoride, shows no visible change. So add named acid to all three, add water / make into solution, add silver nitrate solution. Sodium carbonate will fizz with acid. Sodium chloride will give white precipitate with silver nitrate solution, or silver nitrate, and then sodium fluoride shows no visible change. Stage 3, the equations. I was about to say ionic equations, but no, the equations. Stage 3 equations. So I've got sodium carbonate plus named acid, so say HNO3, nitric acid, and what's going to happen? I'm going to form 2 sodium carbonate NaNO3, 2 NaNO3, I need a 2 here, plus carbon dioxide plus water. And then the other equation, sodium chloride plus AgNO3. Just your displacement, right? AgCl plus NaNO3. So both of these are the same, like gets displaced, right? But in this case, because I've got Na2, it's going to be 2 NaNO3, CO2 per station, and then you need 2 here. Question 5 states the time to the nearest minute when equilibrium was established. 3 minutes. Reason being, explain my answer, because at equilibrium, what's the key factor at equilibrium? Rate of forward reaction equals the rate of backwards reaction. Hence, concentrations of O2 and SO3, they're not the same, they just remain constant, and you really need to say that. The concentration of O2 and SO3 remain constant. Let's get on the graph to show how the concentration of sulfur dioxide changes over 6 minutes at temperature T1, and sulfur dioxide sulfur dioxide I want to see sulfur dioxide change over T1. It looks something like this then. And again, at 3 minutes, equilibrium is established because these concentration of SO2, O2, and SO3 remain constant. Temperature was changed to T2. Mixture left each establishing equilibrium. New equilibrium concentration of sulfur dioxide is going to be 0.07. Initially here it's 0.1. So if I've got 0.07, I've got fewer more concentration of sulfur dioxide. Explain which one is the higher temperature. Well, forward reaction, it tells me in the question, is endothermic because the delta H is positive 196 kilojoules mole per minus 1, endothermic. Right? So if the forward direction is endothermic, if I increase the temperature, it's going to shift in the endothermic direction to oppose the increased temperature, and therefore SO3 will decrease. So which one is the high temperature? T2. T2. Reason being is that equilibrium has shifted to the right hand side /forward reaction in endothermic direction to oppose the increase in temperature to decrease temperature. Perfect. Question 6. Define the term relative molecular mass. Relative molecular mass is the average mass of a molecule on a scale. Average mass of a molecule of an atom on a scale where an atom of carbon 12 is 12. Use experimental results to determine relative molecular mass of Y. So I'm going to use PV equals nRT. N equals PV divided by RT. N equals the pressure in pascals, 102,000. Times by the volume in meters cubed, 85 times by 10 to the power minus 6, divided by a million. Alright, 8.31 times by temperature. And in Kelvin, 98.1 plus 273, 371.1. And then I can also work out the mass of liquid Y. Then I'm like, okay, I've worked out the mass. This will give me the moles. Moles is mass over MR. MR is mass over the number of moles. Now work out the number of moles. So 102,000 times by 85 times by 10 to the power minus 6 divided by 8.31 times by 371.1, and then the mass 0.21 divided by number of moles, 75 is the MR. Rounded to significant figures. Yeah, that was 75. But in reality, I should probably say 74.7, but 75 is perfectly fine. Some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside the oven. Explain how this would affect the volume of MR of Y. Calculated MR value would be greater than the actual MR as lower volume recorded. Because think about it, some of the liquid injected did not evaporate because it dripped into the gas syringe. So that tells me lower volume was recorded because it didn't evaporate, it dripped out. And therefore what happened to the MR? Well, the actual MR, our calculated MR value is greater than the actual MR value. Lower volume recorded, MR, lower volume recorded, therefore MR would be greater than the real MR because lower volume recorded, N equals PV divided by RT, and smaller number of moles, therefore smaller MR, therefore calculated MR is actually greater than the actual MR. This is the oxidation state of chlorine HClO and oxidation state of chlorine and HCl. HClO, that's -1 obviously. This one, that's +1. Give two half could show oxidation reduction processes that occur in this redox reaction. So let's think about it. I'm going from oxidation. Well, the oxidation state of chlorine in HClO is +1, so I'm going from chlorine to HClO, and then the reduction is Cl2 to HCl. So that's how you need to think about it. Why is it part 1 ask me to do oxidation state, then part 2 give 2 half equations? So it's going to be Cl2, the oxidation, a high oxidation state, so HClO. I need a 2 here, and then I need a water molecule here, and then that is completely balanced. No, it's not. Is it? No, I need 2 H2Os. Then I've got 2 oxygens. I've got 2 H2Os, and I need to add 2 H pluses here, and then therefore 2 E minus here. Cl2 plus 2 H2O, 2 HClO plus 2 H plus 2 E minus. Then the reduction half equation, I'm going to go from chlorine to HCl. So we'll go from 0 to -1. That's reduction. Well, first things first, I've got 2 chlorines here, so I need a 2 here. Then I've got 2 HCl here, so I need to add a water molecule here. Yes. But I've got oxygen molecule here, so then I need to add an water molecule here, then add 2H plus 2E minus. Oh, where did I get, oh my days, what is wrong with me, man? Where did I get water from? Yeah, let's do both of these again. I'm usually quite good at these oxidation half equation, but this case, it's not really telling you what you're going from to do. You need to do it yourself, and I think that's a slightly harder part. So the oxidation, I'm going from Cl2 to HClO, 0 to +1. I need 2 here, then I need to add 2 H2O molecules here, then I've got 4 H pluses, I need to add 2 H plus here, plus 2 E minus, so charges balance out. Reduction half equation, Cl2 to HCl, 0 to -1. Well, then I need a 2 here, and then I've got 2 H pluses, so then I just add 2 H plus 2 E minus. What I was thinking about is adding water, because I was like, you can only add water molecules for H pluses. No, you add water molecules for oxygens. If you need to add H plus ions, you just add H plus ions, and that's something I just completely forgot. But yeah, Cl2 plus 2H2O, 2HClO plus 2H plus 2E minus, Cl2 plus 2H plus 2E minus to form 2HCl. Plus 1 minus 1. Give me an equation for this reaction between chlorine and sodium hydroxide. Now this is an equation you do need to memorize off by heart. You definitely do. There you go. Cl2 plus 2 NaOH to form NaCl plus NaClO plus H2O. Question 7.4. Seven point four. Calculate the mass in milligrams potassium iodide interact with all the ClO minus ions. I know ClO minus constitution of this potassium iodide into this much of bleach solution. So I can find a mole of potassium iodide. I want to find the mass of some of the bleach solution containing this much. Now I find out the moles of the bleach solution of ClO minus. Then I can find out the number of moles of the potassium iodide, and then I can do moles of mass of MR, mass of mole time by MR. Now if we look at a mass and then time by 1000 to convert into milligrams. Okay, let's just do that. So 20 divided by 1000 times by 0.0109 then that is CLO minus, and then times by 2. Then I'm going to do moles of mass of MR. The mass is the moles times by the MR, potassium iodide, which is just Ki, which is going to be, I don't know the MR of iodine, I'm pretty sure it's pretty high. And 66. Then I get the mass in grams as 0.072376, and times by 1,000 to milligrams, 72.4 milligrams. I didn't show any work for this case, I just did it again. So moles, concentration volume, get the moles of this, 1 to 2 molar ratio, find out the moles of this, mass in moles times by MR, then you work out the mass in grams, and times by 1,000 to convert from grams to milligrams, times by 1,000. Give one observation during this reaction. Let's say colorless solution turns brown. Solution. Question 7.5, we equation for decomposition of potassium chlorate, KClO4 to KCl, and I'm going to include all the state symbols and all that, plus 2O2 gaseous oxygen gas, obviously. Calculate enthalpy change for this reaction. So enthalpy change, it is formation data. That little F tells me it's formation data. So enthalpy of products, KCl. So, and obviously oxygen by itself is 0, so we don't care about that. Even though it's got 2 moles, we don't care about it. So enthalpy of products minus 436 minus enthalpy of reactants minus 434. That is the same as adding, so then it's going to be minus 2 kilojoules per mole to power minus 1. Question 8.1, calculate mass in kilograms of one ion of 79 Br plus ion. Okay, so what I'm going to have to do is going to have to do 79 divided by Avogadro's constant, and then whatever I get in the calculator, divide by 1,000. Don't do it all in one go, just do it step by step. 79 divided by 6.022 times by 10 to the power 23, then divide by Avogadro, then divide by 1,000, and I get 1.31 times by 10 to the power minus 25 kg. 1.31 times by 10 to the power minus 25 kg. Calculate time taken for the 81 Br plus ion to travel through the same flight tube. So what I need to look at is what I'm going to start doing probably whenever I get these type of questions is write down everything. Like write down Ke, M, velocity, distance, time, and then tick it off once you've got it. Because that will give you like consideration where the mark's going to go. A mark for working this out, working time out, then working distance, and then working out something. For example, so the time taken. Time is distance divided by velocity. I just rearrange this equation. Do I have the distance? Yes. Do I have the velocity? No. So let's work out the velocity. Square root of 2ke divided by m. Do I have the kinetic energy? No, I don't even have the kinetic energy. Okay. So what I'm going to have to do first, instead of that, work out the kinetic energy. So it's going to be 1 over 2, bracket my answer, times by the velocity squared, and velocity is just distance divided by time, so 0.950 divided by time, 6.69 times by 10 to the power minus 4 squared. Once I've got the kinetic energy, then I can work out the velocity. For the 81 Br plus ion, I don't care about 79 Br plus ion. Kinetic energy for 79 Br plus ion and that, yeah, because all of the ions will accelerate to the same kinetic energy, and that's really important. Because if you assume that, you need to assume they're obviously the same. If you assume they're different, then you won't be able to solve it. So they both have the same kinetic energy. So now I use square root of 2ke, 2 times by my answer, divided by the mass of the 81 Br plus ion. 81 divided by 6.022 times by 10 to the power 23 times by 1000. That's the velocity. Then the time is the distance, 0.95 volt, divided by the velocity, and I get 6.777 times by 10 to the power minus 4 seconds. So what does the marking says? It says find out the velocity, then find out the kinetic energy, then find out the velocity of the 81, and then you can work out time. Perfect. Exactly what we did basically. Explain how the ions are detected and relative abundance is measured. Ions are detected when ions hit the detector / negative plate and gain an electron. Relative abundance is proportional to the size of the current flowing the detector. So ions are detected when ions hit the detector / negative plate and each ion gains an electron. A relative abundance is proportional to the size of the current flowing in the detector. Question 9.1, draw the shape of KrF2 molecule. Oh, KrF2. Okay. Now Kr is going to have one lone pair of electrons there, one lone pair, and one lone pair here. The name of the shape, linear. The bond angle, though, well, then the bond angles, yeah, so it's going to be 180 degrees, even though it's got all these bonding lone pair. The two lone pairs of oxygen and the oxygen atom molecule, oxygen and fluoride. Explain how the lone pairs of oxygen atom influence bond angle of oxygen and fluoride. Two lone pairs of electrons. So let's say lone pairs repel more than bonding pairs of electrons, or lone pairs repel more than bonding pairs of electrons. We could say probably both. Let's just say both, and then say that then the bond angle is reduced by 2.5 degrees times by 2. So lone pairs repel more than bonding pairs. Bond angle will be lower. Oxygen difluoride than regular tetrahedral molecule. Silicon tetrafluorides tetrahedral molecule used to have an intermediate form SiF4. It's not going to be dipoles, complete symmetrical as van der Waals forces. And the idea that uneven distribution of electrons in one molecule induce a dipole in neighboring molecule. Symmetrical molecule, so dipoles cancel out. Now there's another case where I've seen a question like was explain how permanent dipole forces arise, and for permanent dipole forces we say uneven distribution of electron in one molecule and just dipole in the neighbor molecule. Then you say, I think unsymmetrical molecules to dipoles don't cancel out. There's a temporary attraction between delta positive and delta negative. So even distributed electron molecules, just dipole neighboring molecules, symmetrical dipole slash dipoles cancel out. And there you go. And that is the end of section A.